Hi guys, welcome to Knowledge Base. In this video, we are going to look at the concept of linear expansivity. If we have a metal rod as shown on the screen now, let's assume that the length of this rod is given as L1, while its temperature is θ1. It simply means this is the initial length of the rod, where the initial temperature of the rod is θ1. If we heat up this rod, probably by keeping it under the sun or by heating it in a flame, the rod will expand and then we will have a rod such as this. It means the rod has expanded in length. So we can say that the length of this rod is now L2 when the temperature changes to θ2. So it was a scenario where we have the original length as L1 and the temperature of the rod as θ1. However, when the temperature increased from θ1 to θ2, the length also increased from L1 to L2 because of expansion. Now, the difference between this length and this one is given as the change in L, or the change in length, which is this portion here. This symbol, this triangular symbol here, is the symbol of change in science, as used in sciences, physics, mathematics, chemistry, and what have you. So the triangle represents change, and it's a symbol that is called delta. So the difference in the length is this portion here, known as delta L, or you can simply say the change in the length or the increase in the length. You will agree with me that the increase in the length is simply the difference between this final length and the original length. So we can say that change in length, or delta L, is L2 minus L1. And that happens because the temperature changed from θ1 to θ2. So the change in the temperature is also θ2 minus θ1. So this scenario we've described is simply explaining the concept of linear expansivity. So what is linear expansivity? First of all, the word expansivity means expansion, something that is increasing. Linear simply means the expansivity or the expansion is happening in a straight line. So as you can see, a rod increases in length linearly. So this scenario is describing linear expansivity because the length is changing because of expansion. Now, what is linear expansivity? Linear expansivity is therefore the change in length of a material as a result of change in temperature, and it is mathematically expressed like this. Linear expansivity is given as alpha. This symbol is alpha, and it's the symbol of linear expansivity. So mathematically, linear expansivity alpha is given as the change in the length divided by the original length times the change in the temperature. So technically speaking, we will define linear expansivity as the change in length per unit length per change or per degree rise in temperature. But literally looking at it, we can say linear expansivity is simply the change in length that happens to a material as a result of change in temperature. So now that we've established this equation, we can take note of it as an important equation that can be used to solve problems under linear expansivity. Now, what is the unit of linear expansivity alpha? The unit of this can be derived from this equation. If you look at our first set of videos where we talked about derived units, you will understand how to derive units of quantities. If you look at this formula very well, change in length is a length this is also length. So if both cancels out each other, you will just be left with change in temperature at the denominator of the fraction. And the unit of temperature is Kelvin. And because it is at the denominator, it is simply referred to as per Kelvin, per, P-E-R, to represent the denominator of a unit. So the unit of linear expansivity is per Kelvin, K for Kelvin, and this is how it is represented in index notation. This linear expansivity is a constant value for different material. It is what describes how different materials expand, and it is constant. From experiment, it has been proven that iron, for instance, does not expand as much as brass if both of them is subjected to the same temperature. The reason is because from experiment, the value of alpha for brass and alpha for iron has already been proven. And these are the values. Brass, the linear expansivity of brass is given as 0.000018 per K, while that of iron is given as 0.000012 per K. And this simply tells us that brass being 18 and iron being 12, brass expands more than iron, and they are constant value. Because they are constant value, most of these common metals already have their value determined in the laboratory, so we often do not calculate for their linear expansivity. Rather, we could be asked to calculate for any other thing by making them subject of the formula from this equation. For instance, you could be asked to calculate the change in the length, the original length, the final length, the change in temperature, and what have you. So we are just going to derive quickly the formula for the final length of a material if we know the linear expansivity of that material. So to get that, from here we can simply replace delta L by L2 minus L1, which is the change in the length, so that the linear expansivity alpha becomes L2 minus L1 all over L1 times temperature change. If we cross multiply here, L2 minus L1 is simply alpha dot in mathematics means times alpha times L1 times change in temperature. To make L2 solve the formula, minus L1 crosses the equation sign and it becomes L2 equals to L1 plus this. L1 is common to both sides on the right hand side. We are just going to factorize it out, and when we factorize it out, L2 becomes L1. L1 divide L1, what is left is 1. L1 will cancel out this L1, and what is left is alpha times change in temperature. So this formula is also an important formula that we can use to determine the final length of a material as a result of expansion. So these two formulas are key. This one and this one are important in solving problems involving linear expansivity. I hope you enjoyed this video. In our next video, we shall look at a simple calculation on what we've explained, and I hope to see you in the next video. Thank you very much for watching.